Right now, invisible waves are passing through the walls of your house, through your body and through the air around you. You can't see them, you can't feel them, but they're carrying every video, every message, and every web page you've loaded today. Today, you're going to see exactly how Wi-Fi works, from start to finish in simple terms anyone can understand. Let's start with the moment you tap something on your phone. When you open an app or a web page, your device doesn't talk directly to the internet. It can't. Instead, it turns your request into pure binary code, long strings of ones and zeros, and packages that code into small digital containers called radio frames. Each frame carries the actual data, plus a label showing where it came from and where it needs to go. Your phone doesn't send these frames out into the world randomly. It sends them to one specific device sitting somewhere in your house, your wireless router, more accurately called an access point. That little box on your shelf is doing more than you'd think. It's a modem, a router, a switch, and a firewall all sitting inside one plastic case. But here's the problem: ones and zeros can't just float through the air on their own. They need a vehicle. That vehicle is a radio wave inside your router and your phone. A component generates a high-frequency electrical signal called a carrier wave, oscillating at either 2.4 billion times per second or 5 billion times per second, depending on the band being used. Your device's data doesn't replace this wave, it rides on top of it through a process called modulation. All the Wi-Fi systems spread the data across a wide channel for reliability. Modern Wi-Fi uses a smarter method, splitting one wide radio channel into dozens of smaller, tightly packed channels and sending pieces of your data across all of them at once, in parallel, instead of forcing it all through a single narrow stream. Before that signal ever reaches the antenna, it passes through a tiny but critical piece of hardware called the RF front end. Think of it as a signal's final preparation station. One part locks onto the exact frequency needed, another part boosts the modulated signal up onto that frequency. Then a power amplifier takes the now-shaped signal and pumps it up to a strength high enough to actually reach across a room or across a house. Only then does it hit the antenna, and the moment electrical current surges through the antenna, something remarkable happens. It creates invisible electric and magnetic fields that detach from the metal and radiate outward into the air as a real physical electromagnetic wave. Now that wave is on its own, traveling out in every direction from your router. Picture it like ripples expanding from a stone drop in a pond, except in 3 dimensions, expanding as a sphere instead of a flat circle. As that sphere grows larger, the same amount of energy has to stretch to cover more and more space. That's why the signal on your phone gets weaker the farther you walk from your router. The energy isn't disappearing, it's spreading thinner. The two main Wi-Fi bands behave differently as they spread. The 2.4 GHz band has longer, lazier waves that bend more easily and travel further, often several hundred feet. The 5 GHz band has shorter, tighter waves that carry more data, but lose strength much faster, often struggling past 200 feet. And distance isn't the only obstacle. As these waves move through your home, they run into walls, doors, furniture, even you. When a wave hits something hard and metallic like a refrigerator or a steel beam, it bounces off, sometimes creating multiple delayed copies of the same signal arriving at slightly different times. A problem modern routers solve using multiple antennas working together. When a wave passes through glass or plastic, it bends and slows, weakening the connection. When it meets a sharp edge, it can bend around the obstacle entirely, letting your Wi-Fi reach around corners, though weaker than before. And when it meets something rough or oddly shaped, like a chain-link fence or a cluster of furniture, it scatters into a dozen weaker waves heading in random directions. But the biggest energy loss doesn't come from bouncing or bending, it comes from being absorbed. Here's where it gets strange. Some materials don't just block Wi-Fi, they eat it. Water is the biggest culprit. Water molecules have a lopsided electrical structure, a tiny positive end and a tiny negative end, and they naturally try to twist and align themselves with the rapidly flipping electrical field of a passing Wi-Fi wave. but that field is flipping billions of times per second, faster than the water molecules can keep up. That mismatch creates constant molecular friction, and friction always creates heat. The wave's clean, organized energy gets converted into random molecular jiggling, and your body is roughly 60 to 70% water, which means you standing in a room are an active Wi-Fi absorber. Simply holding your phone can weaken its own signal. A person standing directly between a router and a receiver can cause a significant additional drop in signal strength. This is exactly why office buildings mount their Wi-Fi access points on the ceiling, up and out of the way of the very bodies trying to use them. Walls cause a similar kind of absorption, just through a different mechanism. Materials like concrete and brick contain tiny charged particles that get pushed back and forth by the wave's electrical field. As those particles shuffle around inside the material, they collide with its internal structure, and once again, that motion turns into heat. A single layer of drywall barely slows a signal down. A thick concrete wall can block the vast majority of it. Eventually, whether through spreading, bouncing, or absorption, a Wi-Fi signal grows too weak to detect. It doesn't vanish, it simply fades below the noise floor, the point where a receiver can no longer tell your data apart from random background static. So could someone build their own Wi-Fi system from scratch? Partially, yes. Building a basic radio transmitter at home is genuinely possible. Hobbyists have done it for decades using simple low-frequency circuits, but building an actual Wi-Fi transmitter completely from raw components is, for all practical purposes, impossible for an individual. At the gigahertz frequencies Wi-Fi operates on, timing has to be accurate down to fractions of a billionth of a second, and even a slightly too long wire on a circuit board can throw the whole system out of tune. This is why virtually every Wi-Fi device on Earth uses the same trick. A small pre-built chip that already contains a certified radio system, ready to be dropped into a larger design. What is genuinely accessible to a hobbyist is building your own smart router using something like a small computer, flashing it with free open source software, and turning it into a fully customizable network gateway, or even building a homemade directional antenna out of something as simple as a metal can, precisely sized to focus a weak signal into a stronger, more directional beam. And under United States law, small-scale, low-power, homemade radio experiments like these are actually legal as long as the builder doesn't sell them, doesn't interfere with licensed radio services, and stays under strict power limits. So the next time your video buffers or your signal drops walking into another room, you'll know exactly what's happening. A wave carrying your data is spreading, bending, bouncing, and slowly being swallowed by the water in the walls, the furniture, and even you until it either makes it to its destination or fades quietly into the noise. That's how Wi-Fi works from start to finish, in simple terms anyone can understand.